All right. Another morning. We're getting pretty close, I guess, to reading week. So last day of class before a week of, I don't want to say a break perhaps, but mad rush to maybe catch up on stuff if you've fallen behind at some point. It's also a bit of a shame to start a new topic right before a week so you can forget everything that we introduced today and then try and get back into it on Monday after the break. But today we're moving on from compression members, which we wrapped up last day with an example and a discussion on how we might select a compression member, a cross-section, usually a W-shape or an HSS, to work as a column or potentially as a compression brace, if that was the situation we've got. Just a quick moment to recap what we've talked about so far in the course. We started with some structural analysis. We started talking about how buildings worked. We looked at the transfer of loads, both lateral and gravity loads, to figure out what members might be beams, what members might be columns, what members might be braces. And from the loads, we did some structural analysis reinforced by doing some computer work in the labs in STADPro. And we looked at the design of tension members, how they would get ripped apart in tension, some serviceability considerations, and finally how to pick a tension member that will work for your brace in a building. Then we talked about compression members that primarily buckle. They're a little bit simpler, generally speaking, than tension members because the limit state is generally buckling. But local buckling can affect the overall compressive resistance. And we looked at where the compression members might be in our structures, what the effective lengths might be, and we wrapped that up last day with how we'd pick a cross-section to work as an efficient column. Now we're moving on to flexural members. And flexural members, for the most part, are beams, but we'll see there's at least one other special case where we're not looking at a beam, and we'll talk about that next day. But basically what we're going to be focusing on for a while is something called braced bending. We're going to see that there are a couple different types of beams in our structures. One is called the joist, which we looked at calculating the loads on using the tributary width approach. They're going to be braced and bending by the steel deck, and I'll tell you a little bit about what that means. And there are also girders, and girders take the load from the ends of the joists. They're braced only between the locations where the joists frame into them, and so they're not attached to the steel deck. And we'll see what the influence of not having the girders here fully braced against something called lateral torsional buckling means, and we'll talk about unbraced bending after the break. We'll also talk about column base plates that aren't shown there, and we'll talk about shear resistance and deflection, which are things that we would expect to talk about for beams because we draw shear and bending moment diagrams, and we typically calculate the deflections of our beams. So for the next few lectures, these are the kinds of things we're going to be focusing on. We're going to focus on how beams bend or shear too much. Those are typically the ultimate limit states in terms of strength. We want to make sure the shear resistance isn't exceeded, the bending resistance isn't exceeded. And we're also going to look at serviceability limit states, which are basically associated with deflections of beams in our structure. If they flex too much, that'll cause issues for floor vibration. It will cause delamination or cracking of floor systems, and it could potentially cause warping of door frames and stuff, which is bad for egress, especially in fire situations. So we're going to look at expressions that look something like this. We're going to be calculating moment resistance of our beams. We're going to see when we can take it as an expression that looks something like we see on the right here, phi ZFY. Today we're going to talk about what Z means and when we use Z versus another parameter called S. And all the time our moment resistance has to exceed our factored bending moment. Okay, so on assignment 1 you calculated some shear forces and bending moments on your beams. On assignment 6 you'll do the factoring in accordance with the load combinations from NBC to get your factored moment. And then we're going to figure out how to pick a beam with adequate moment resistance so that this inequality is satisfied. The second equation looks kind of scary. It looks kind of like the equation that we saw for torsional buckling in compression members. And this is for something called lateral torsional buckling. And you might not know from mechanics of materials or structural analysis or any courses prior, but beams can buckle. And that seems a little bit weird. But in a couple lectures, I'll tell you about how beams can buckle and how this equation will help us in calculating the moment resistance when beams want to buckle sideways. I'm going to talk about shear resistance. This one's pretty straightforward. We'll spend a lecture talking about that, in addition to talking about the deflection calculations and what the limits on deflections might be for these types of systems. Okay, so today we're basically just introducing the ideas behind flexural members. The backdrop here is a couple different kinds of flexural members. So we can see in this framing arrangement, we've got some joists here, right, which are supporting the steel deck, and they're framing into the girders. We're going to focus today on some stuff that we'll be using to quantify the strength of joists, and we'll talk about how we modify that to calculate the strength of girders. Basically, we're just looking at situations like this. We'll remember that joists basically carry a uniformly distributed load on them. Those uniformly distributed loads turn into reactions at the connections. Those reactions are forces on the girders. And so we're going to see that because the joists are attached to the steel deck, normally there's some kind of fastener from the steel deck to the top of the joist. That's going to stop the beam from wanting to twist sideways, and so we're going to focus on calculating the strength of beams in that kind of situation today. But we're also going to look at situations where the beam is not continuously attached to the deck, and we're going to see that for this situation, for the girders, for example, the fact that they're not braced continuously along the top flange will result in potential for some twist of that member. Overall, though, today we're going to focus on the bending of braced members, and I'll talk about when we can use something called the yield moment and the plastic moment when calculating the moment resistance. So basically after this, you should be able to differentiate between a yield moment and a plastic moment. You've probably talked about yield moment even though you didn't know about it in 2023. And we're going to talk about that in the context of steel design in this course. You should be able to determine the section class of a steel section under flexural compression based on its susceptibility to local buckling. We talked about local buckling before for compression members. We're going to see that because beams also experience compressive stresses, right, either in half of the web or in the flange, that's under compression, there's going to be the potential for local buckling there as well. And finally, the goal is to be able to calculate the factored moment resistance of a laterally braced or supported beam, and I'll tell you a little bit more about what that means throughout the lecture today. Are there any questions about these three things before we continue with the technical material for the morning? Great. So again, going back to 2023 stuff, and in fact, we used this equation in assignment 0, right, lab 1. Showed you how to calculate bending stress. And when we're calculating bending stress, we know that there's a neutral axis where there's 0 strain and 0 stress. There's a point at the extreme the extreme fiber in compression. We're going to have a significant amount of stress. The extreme fiber in tension, we're also going to have a significant amount of stress. And if it's symmetric about the neutral axis, then the stress in compression is going to be equal to the stress in tension. And we used this equation. You might have seen something like sigma is my over I. Typically in steel design, we tend to replace sigma with a little f, and B is for bending. And the maximum bending stress would be the moment on the beam times C, which is the distance to the extreme fiber. Right? Y is any distance from the neutral axis to the extreme fiber. C is the maximum distance divided by the moment of inertia. So when is a beam going to be acceptable in terms of bending strength? If we can calculate FB max, is there a limit we should probably impose on that maximum bending strength or stress that we could use to quantify moment resistance, for example? What should we be limiting the stress on our section to? Any ideas? Probably the yield strength, right? We often talk about preventing yielding of the cross-section. And so we could potentially say, okay, we want FB max to be less than or equal to the yield moment, the yield strength, and perhaps even with the resistance factor there, but we'll talk about that a little bit later. So we might say, okay, we want to figure out what moment is going to cause this beam to yield, and basically that's the point or the moment at which we generate a flexural stress equal to Fy. Right? So we basically say, okay, FB max is equal to Fy. We saw this expression before. The maximum bending stress is the moment times the distance to the extreme fiber over Ix. If we set that equal to Fy, we're basically going to say, okay, there's a certain moment that we're going to call My. That's the moment that causes the beam to start to yield. And we're going to call that in this course the yield moment. Okay, and that's going to be different from another moment that we'll talk about in a minute. So there's a moment that will cause the FB value to be just equal to Fy. That's the yield moment, and we can calculate it by rearranging the expression here to get my from Fy is equal to myc over Ix. So the moment we could calculate, the moment that would cause yield would be yield stress times I divided by C. And I'm going to define a new parameter that I don't think you've seen before, and that's okay. I'm going to define a new parameter here called the elastic section modulus. And that's simply going to be the moment of inertia divided by the distance to the extreme fiber. Okay, and we're going to call that value S in this course. So what we're going to see basically is we have this cross-sectional parameter S, the elastic section modulus for any kind of beam. It can be calculated quickly. If you can calculate Ix and you know C, you can calculate S. And where do you think you could find S values if you didn't want to calculate them for a certain cross-sectional shape? In the handbook, right? So we're fortunate that all of these shapes that we deal with in steel design are pre-rolled. We've got a W, I don't know, 250 by 33 or something. You just go to the handbook and you look up the value of S. And once you find S, you can calculate the moment that would cause that beam to yield by multiplying that value by the strength of the steel in the beam. Okay, so nothing really new here. Basically just stretching your minds a little bit beyond 2023 to calculate a yield moment using this new parameter S. And there's going to be a section modulus that corresponds to bending about the strong axis as well as bending about the weak axis. Are there any questions about that concept before we continue on? Okay, so this is one moment, right? We'd say, okay, well, if we don't want our beam to yield, we'll probably want to make sure that the moment on the beam doesn't exceed Sx Fy, which gives us the moment that causes the beam to start to yield. We'll see if this works. Oh, pull everywhere is going to shit in my hands again this morning. That's great. Yeah, it is going to. Let's see if we can get this up. Okay, I'm going to say to hell with pull everywhere because it's just whatever. This is the moment that would cause the beam to first start to yield. And so I'll just pose the question to the class. Is that the maximum amount of moment we could ever potentially apply to that cross-section? Or could we apply more? What do you think? Maybe I'll give you 30 seconds to talk about it instead of just posing it to the class. So normally I'd be having about a minute for the pull everywhere. Take 30 seconds. Look at the shape of the stress diagram here. This is the moment that causes the beam to start to yield. Is that the most moment we could possibly apply to that section, or could we apply more? Could probably apply more. I'll ask you why in about 25 seconds. Okay, so there might have been some fruitful discussions, and Katie had said you can probably apply more. Why do you think that is, Katie? Any ideas?
Because this is just the yield strength.
Mm-hmm.
It hasn't reached its ultimate stress yet. So I think that means we could apply more.
So maybe we could apply more, right? Like the steel's not gone, it's not fractured. Maybe we can apply some more. And maybe we can exceed the yield strain and start to go towards FU or something like that, right? That's on the right track. Does anybody else have any comments or thoughts that they want to share? So when we designed our tension members, right, of course we could have let our braces at the cross-section reach the ultimate strength. Part of the problem with that for our braces was once the cross-section yields, basically it's going to stretch uncontrollably, and that can cause lateral instability issues, and that's a problem. But we did let the cross-section reach the ultimate strength at the connection. So maybe you're saying, okay, well, Fy is just the yield strength. I mean, we don't want to damage the beam, maybe under service loads, but if we want to prevent collapse, maybe we can continue stretching the stress beyond Fy. Right? So maybe we could say, well, let's plot the strain diagram, and let's just say, this is the strain, and this is the strain at yield. Maybe we can exceed that strain, right? Maybe we can say, okay, let's try and go a little bit further. The question is, if we go a little bit further, what does the stress diagram look like, right? So we can probably exceed the yield strain and try and take advantage a little bit of the additional strength or some of the ductility of steel. We will go back and remember that steel is a very ductile material, and so within the elastic range it's very strong and it's very stiff, but once it reaches the yield strength, we have a significant amount of plastic deformation that comes from yielding of the steel. And over that distance, there's not a significant increase or any change at all, really, right? Basically, we have Fy for a significant amount of strain, and eventually you might get a little bit of strain hardening, right? So maybe for really, really large strain values, we'll get a bit of strain hardening. And close to the neutral axis, where the strains are still relatively low, we may still be within the elastic region. And so the question is, if for the strain diagram that looks something like this, basically we come down and say, okay, in the regions where the strain exceeds the yield strain, the stress in that region is going to be mostly constant, and it's going to be equal to Fy. And within the region where we are still within the elastic strain, we're still going to have a linear elastic stress in that cross section. Okay, so that might look something like this, right? We can say, okay, well, we'll exceed the yield strain at the extreme fiber, and we'll have the yield strain exceeded until we're maybe a distance something like this. We could, from equilibrium, figure out what the moment is, right? We could take this area, and we could multiply that by the yield stress, and we'll have a force and compression at the top. We'll take this area at the bottom, that's in tension, it's fully yielded, and so we could take a force in tension at the bottom. And then we've got a little bit of tension here still, but it's in the linear range, but we could still, for that rectangle, figure out where the center of the force is, figure out a tensile force, and say for the same thing in compression, a little bit of compression here, a force in that web that comes from that linear distribution of stress. And from equilibrium, we could figure out what the moment on the beam at that moment in time to cause that stress distribution might be. Now, steel is really ductile, right? So we saw that this is sort of the linear elastic range, and then we have a yield plateau. Well, the yield plateau can continue on for a significant distance, right? And so what we can actually do is continue to increase the strain on our beam until we get to a point where we're not going to get a significant amount of additional bending moment strength out of that beam, right? So this is basically the linear elastic part, this is the yield plateau, and this is the region where we start to get a little bit of strain hardening. This is what we call the plastic limit for the beam, and what we're going to do to simplify this case a little bit for us is we're going to ignore the little bits of strain hardening out here, and we're going to assume that everything above the neutral axis has yielded, and everything above or below the neutral axis has yielded. Now, it's impossible, right, for this to really be the case because you cannot reach the yield strain at the point of zero stress. But if we ignore the strain hardening parts and we assume that the part above and below the neutral axis has yielded, then we can simplify the stress distribution using what we call the plastic stress distribution. Okay, so we basically assume everything below the neutral axis is plastic, everything above the neutral axis is plastic, and what this corresponds to is the achievement of what we call plastic bending moment. Okay, so everything above and below the neutral axis has plastified. And there's no simple equation that we can just use like my over I. That's not valid here anymore, right? This equation, FB, is my over I. That's only valid for linear stress, right? For linear stress and strain distribution, we can use my over I, but we cannot use that anymore. At the same time, it's still a pretty simple problem because it's a uniform stress. We know how to calculate the force that might be in the flange or in the web above and below the neutral axis here. And so basically what we're going to do is break this up into the force in the flange at the above and below the neutral axis. And we're going to say, okay, there's a force here that's equal to the area of the flange, which is BT times Fy. There's a force in tension down here. That's the area of the flange times Fy. And then in the web, there's a force in here. And if we use the clear distance h, this is going to be h times W over 2. That's the area of the web times Fy. And down here as well, HW over 2 times Fy. Right? So if we assume that the steel above and below the neutral axis is perfectly plastic, then we can use the stress times the area to get the forces. And once we have forces, then we can just add up the relative moments, assuming that we have a moment couple. Right? Basically, we've got WH over 2, 0.5 WH. The distance between those two equal and opposite forces is 0.5 h. And then we've got the flange forces, which are BTFY. And the distance between those two forces is d minus t. In statics, you talk about moment couples, right? I'm assuming you've talked about moment couples. If you have equal and opposite forces, the moment is the force times the distance between the forces. And so if we apply that similar concept here, then we end up with the moment is bt times d minus tfy plus 0.25 wh squared fy. And if we factor out the fy part, we get a new cross-sectional property that we're going to call Z, and that's the plastic section modulus. Okay, so we have now an elastic section modulus that corresponds to first yield at the extreme fiber, and now we have a plastic section modulus that corresponds to complete plastification of the cross-section above and below the neutral axis. Okay, does anyone have any questions about that concept before we continue? Now the question is, which one of these moments do we use to design our beams, right? Before I get into that discussion, I'll show you what this looks like, right? Why can we take advantage of this perfectly plastic section behavior, and how does it help us increase the strength of our beams? This is a quick video. This is literally just a rectangular cross-section. Okay, so if we were to look at the section here, it's rectangular. And basically, I've just applied a uniformly distributed load over this beam. Okay, this is just a numerical analysis with a yield strength of 50 KSI. That's what's shown here, 50,000 PSI. And what you're going to see is how the beam behaves as it starts to get more and more load. And you're also going to pay attention to where the red is. Okay, the red here is going to indicate yielding of the cross-section. And so as I play the video, pay attention to where the red is and pay attention to how the beam deflects as the stress changes. Okay? So I don't know why it stopped there. That's actually great, though. I'm happy it stopped there. Because what we're going to see here is we're just starting to achieve the yield strength above and below the neutral axis. The beam is still deflecting the way that we would expect it to deflect. And so it's still working in the elastic range. And I don't know. There we go. And once we exceed the yield moment, we start to plastify more of the cross-section above and below the neutral axis. And it doesn't behave elastically anymore. In fact, it starts to bend more like a V. Right? So there's some elastic deflection from the elastic behavior, and then there's basically a V-shaped deflection that comes from the fully plastic behavior of that cross-section. Basically, this is the kind of behavior we want to prevent, right? A collapse. This is the kind of thing that will cause the collapse of the floor system because there's no more strength in that beam. Whereas if we allow it to yield a little bit, it's still safe. It hasn't collapsed yet. And so that's why we can take advantage of the plastic modulus to increase the moment resistance a little bit. And I'm going to show you basically what the relative difference would be for a rectangular section. What I'm showing here is the moment that was applied to the beam relative to the yield moment. And so at the yield moment, we get this kind of behavior, starting to yield at the extreme fiber above and below the neutral axis. And then as we yield more and more of the cross-section, we start to lose stiffness, and then the strength of the beam plateaus at this plastic moment resistance. And for rectangular beams, we can get up to 50% more moment out of the cross-section when we allow the beam to achieve the plastic moment resistance. Okay, so that's a significant increase that allows us to take advantage of the ductility of steel to reduce the amount of steel we put in the building and still have a safe design. At the same time, the sections that we tend to use aren't really rectangular. We tend to use shapes that are I shapes or wide flange. And the Z to S ratio, which we sometimes call the shape factor, MP over MY is also equal to Z over S. And so for the rectangle, we can get 50% more strength. And that's always the case for rectangles. For wide flange sections where the flanges are different sizes or different thicknesses, the web is different depth and different thickness, the ratios change. It's not a constant value for I shapes. But we tend to be able to get about 12% more strength when we consider the plastic moment capacity relative to the yield moment capacity. Okay, so that's not as much as the 50% that we get for a rectangle, but it's still a little bit more economy that we can squeak out of our wide flange shapes. So we have the concept perhaps of yield moment, and that's the point where the beam is still elastic, but it's just starting to yield. And we have the concept of plastic moment, where we've plateaued the strength of the beam. We get excessive movement that results in partial collapse or full collapse of the structure. Does anyone have any questions about the concept or the difference between those two moments before we continue on? Okay, so we still haven't answered the question yet. When can we use the plastic moment, and when can we use the yield moment? Ideally, we'd use the plastic moment all the time. It gets us more strength. But we're going to be limited from time to time by the cross-sectional properties of the beams. And from time to time, we'll have to limit the strength to the yield moment. And for really thin sections, sometimes we even need to limit our moment resistance to something less than the yield moment. Okay? And what I'm going to show you here is basically what we need to do when we're looking at the bending strength of laterally supported members. CSA S16 in clause 13.5 tells us how to calculate the resistance of laterally supported beams, which are basically beams that are not going to twist or deflect sideways, and that's primarily the joists in our structure. It tells us that for class 1 or 2 sections, we can use this plastic section modulus. Okay, we can take the plastic moment resistance. This is basically equal to phi MP. We, again, just look up the section modulus in the handbook. We're targeting a similar reliability index of beta as 3, so we're using the same resistance factor as for gross section yielding and for buckling of our columns, and we've got the same minimum specified yield strength for the steel that we're using. So the question is, what is a class 1 or 2 beam, and what happens if we don't have a class 1 or 2 beam? Class 1 or 2 beams can achieve the plastic moment. Class 3 beams can't, and class 4 beams can't even achieve the yield moment. And basically the reason for that is, at a certain point, the flange or the web may buckle locally before we achieve the yield strength. Right? We talked about this concept when we looked at compression members. If we have compression in the flange and in the web, we're trying to get to the yield strength, but if the flange is too thin or the web is too thin, we're just not going to get there. And we're going to start to buckle the section locally, and that's going to reduce the allowable stress that we can apply to our beam. Class 1 and 2 sections do not experience local buckling before they get to the yield strength, and so class 1 and 2 can achieve the plastic moment resistance. The only difference between class 1 and 2 is that a class 1 beam can sustain that resistance for large plastic deformations. A class 2 beam will get to MP, and then it will start to experience local buckling, and we won't be able to sustain that plastic moment resistance. Class 3 sections can achieve MY, but they're not going to be able to get to the plastic moment because either the web or the flange will buckle locally, and that's going to reduce the moment resistance. And class 4 sections, they're not even going to get anywhere near the yield strength. At an elastic stress below Fy, they're going to buckle locally, and that's going to reduce the moment resistance associated with that cross section. Okay, so My is still an important thing to calculate. We need to calculate My, and as long as we have at least a class 3 section, we can use My. And we can only use MP if we have a beam that's a class 1 or a class 2 section. So the question is, what makes a beam class 1, class 2, class 3, or class 4? And we've already talked previously about slenderness limits, and I'll show you those in a minute. But the one thing I'm going to show you quickly is what we do if we don't have a class 1 or 2 section. We'll see in a minute how to classify the sections, but what S16 tells us is that for class 1 and 2 beams, we can use the Z value to calculate moment resistance. For class 3 sections, we can use the elastic section modulus. But if we have a class 4 section, then we're in a little bit of trouble. So we're not going to talk about situations in this point. Basically, it says for class 4 circular HSS or other class 4 sections, MR shall be calculated in accordance with one of these things. We're not talking about the situation where both the web and flange exceed slenderness limits. I do talk about that in that's more of a cold form thing. We don't talk about that in either course. When the flanges meet the requirements of class 3 but the web exceeds, we're not going to talk about that in this course, but we will talk about it in 5063. The one thing I'll show you here is that if the web is still class 3 but the flange doesn't meet class 3 requirements, we're going to look at basically an effective section modulus in a similar manner as to how we looked at an effective area for the beam, for the compression members previously, and I'll show you how to go through those calculations. Okay, so this all depends on, as you might have guessed, width to thickness ratios. Right? So we looked at width to thickness ratios for compression members. B over T had to be less than or equal to 200 over the square root of Fy for the flange, had to be less than or equal to 670 over the square root of Fy for the web. And that was for members under axial compression only, and we used table 1 to find the upper limits on those. We didn't talk about these parts the other day, and so we're going to say in 11.1.1, for the purposes of the standard, structural sections are going to be designated as class 1, 2, 3, or 4, depending on the width to thickness ratios. Okay, so class 1 sections basically permit the attainment of plastic moment, and you don't have to pay much attention to the subsequent redistribution of, but they can sustain that plastic moment resistance for large plastic deformations. Class 2 sections, we can get there, but we cannot sustain it for very long. Class 3 sections can achieve the yield moment, and class 4 sections will have elastic local buckling before we get to the yield moment. Okay, so those are the things that are mostly important for us to take away, are the differences between class 1, 2, 3, and 4, and that's what this plot is generally showing in terms of the achievement of those moment resistances and how a class 1 section can sustain the plastic moment resistance for large inelastic rotations. We did talk about this the other day in compression members, the maximum width to thickness ratios of compression elements for members subject to axial compression. Those came from table 1, and we've already talked about those. And those of elements subjected to compression and members subject to flexure, or combined flexure and compression, which we'll talk about in a couple weeks, they're going to be specified in table 2. Okay, so table 2 is basically table 1, but now it's a little bit different for the web in particular. And basically the flange is similar to what we saw before. This was square root of 200 over the square, B over T for the flange had to be less than or equal to the square root of to 200 divided by the square root of Fy to use the compression resistance equation without reducing the area. And this is now the class 3 limit for beams. That ratio must be smaller in order to be class 2, and must be even smaller to be class 1. Right? So it has to be, the width to thickness ratio has to get smaller and smaller and smaller in order for it to achieve a class 1, and it doesn't have to be too bad for class 3. Anything that exceeds these limits is going to be class 4, and in that case we're going to have to start modifying the cross-section to calculate the moment resistance. For webs, it's a little bit different. For webs, for compression members, we said, okay, well, H over W had to be less than 670 over the square root of Fy. Here we're just going to ignore for now the terms in brackets, so don't pay too much attention to those. We're not looking at a situation where we have any compression acting on our section. We're just looking at bending. So for columns, it was 670 over the square root of Fy. For beams, it's 1900 over the square root of Fy. Does anyone have any idea why a beam doesn't have to have a web as thick in order for it to achieve the yield strength, for example, compared to what it might be for a compression member? Why are we letting beams have thinner webs to still achieve the yield strength where we needed thicker webs for it to achieve the yield strength for compression members? Why are these ratios different? When we looked at columns or compression members, basically the general assumption more or less was that there was a uniform stress in compression. And if we look at that, this is the flange here, and so if I was to draw it in 3D, right, it would look something like this. So there's the flange, there's the web, and there's the other flange. So the flange, when it's under compression, that's uniform across the section. The whole flange is under uniform compressive stress, right? The stress doesn't change in the flange. And in the web here as well, as long as the stress is uniform, the stress does not change along the height of the web. But if we look at a situation, that's for pure compression. If we look at a situation for bending instead of pure compression, as we've already seen previously, right, we're basically trying to achieve for, let's just say for elastic moment or yield moment resistance. If we look at the difference in the stress distributions in the flange, is the stress distribution significantly different in the flange when the section's under uniform compression compared to the stress distribution in the flange when it's under flexural stress? Is there a significant difference in the stress in the flange at that point in time or between those loads? The answer is no, right? Like it's a slight variation here, but this is more or less uniform compressive stress. This is certainly uniform compressive stress. And so the flange doesn't really have a change in the stress distribution. It's under uniform compression, and so the equations that we use to calculate the local buckling strength of the flange are basically the same for both situations. If we look at the web, is there a change in how the compressive stresses are distributed along the height of the web between the left and right-hand sides? There's a significant difference, right? On the left-hand side, it's 100% compression across the whole height of the web. On the right-hand side, there's some compression, and it's maximum here, but the stress goes to 0 in compression here, and the rest of the web is in tension. It's less likely to get local buckling of that web because there's significantly less compressive stress on that web than there is when it's under uniform axial compression. Okay, so only part of this section is under compression, right? So that's the compressive stress. And not only is the compression over half the height of the web, but the stress overall is half as well. The total compression force on the web in compression is half. And so that changes the amount of total moment that we can apply to the section before we start to get local buckling. Okay, so in this section, H over W has to be less than or equal to 6, I'll erase that. H over W has to be less than or equal to 670 over the square root of Fy, whereas over here, h over w has to be less than or equal to 1900 over the square root of Fy. And in both cases, this would basically make the section class 3. Okay. For the flange, it's the same. B over T in terms of the elastic width, or B over 2T in terms of the flange width, has to be less than or equal to 200 over the square root of Fy for both cases to be class 3. Whereas for webs, because the compressive resistance or the compressive stress distribution is significantly different, then we don't apply the same strict requirement. Okay, we're not really going to look at any of these other situations, though. For I sections bent about the y-axis, it's a little bit different, specifically for the class 3 limit, and that's again because the stress distribution is slightly different. When we have weak axis bending compared to strong axis bending, it's linearly distributed in the flange instead of uniform, but for the other situations, it's the same. Okay, so to classify a section, we calculate the width to thickness ratio for the shape. We calculate the limits for class 1, 2, and 3, and figure out if it's less than this, we've got class 1. If it's between these two values, it's class 2. Between these two values, it's class 3. And if it exceeds class 3 limits, then we have a class 4 section. Are there any questions about what's here in Table 2 and what it means for us before we continue with the last part? Okay. So if we have a situation that we're going to talk about in 3063, in 3063, we're only going to focus on situations where the web is at least class 3. Okay, in 5063, we talk about situations where the web is class 4, but the flanges are class 3. It's quite different in terms of the calculation of the moment resistance. We're going to focus on, in this course, situations where the web might not meet the class 3 requirements. So if the web exceeds if B over 2T for the flange is greater than 200 over the square root of Fy, just like we did for compression members, we're going to calculate an effective flange width. Okay, I think for compression members, I said it was 2 times 200 over the square root of Fy times T. I've just put those together to make 400 over the square root of Fy times T. It's the same effective width. We're going to assume that the web at least meets class 3, and you have to check it, of course. But if it meets class 3, then we can use this approach. So basically what we're doing for compression members, we calculate an effective area. And we plug that into the compression resistance equation to get the compressive resistance. For beams, we calculate an effective section modulus. Okay? The section modulus, again, is just equal to the effective moment of inertia divided by the distance to the extreme fiber, which is d over 2. Right? So this is basically the effective moment of inertia divided by c, where c is equal to d over 2. Okay, so everyone knows how to calculate moment of inertia from statics. We've got the moment of inertia for the web. That's h cubed times the width divided by 12. And then for the web, we have, I guess I'm omitting the moment of inertia of the flange about itself. Basically, when we have really thin plates that are a large distance away from the centroid, if we think about the t cubed b, or the b times t cubed over 12 part, b times t cubed over 12 is not going to give us a whole lot of moment of inertia there. Okay, we compare that to the h cubed w, right? H for steel members is like 50 times w, right? Whereas for flanges, the b is usually something like 15 times t. So if we think of the b times t cubed part over 12, that's not going to get very big very quickly because we're cubing the t, whereas with for the web, we're cubing the h, right? H cubed grows very quickly compared to the width of the web. And so basically in this equation here, you're going to see that I've omitted the bt cubed over 12 part for the flanges, and I'm just including the AD squared component, right? The parallel axis component. And so if we consider only the parallel axis component, we've got the center of the section, we've got the centroid of the flanges, and so we get the area, which is the effective width times t, times the distance squared, which is d minus t. That should be d minus t over 2 squared. Pardon the brackets there. And so d minus t divided by 2 is this distance squared times the area, and then we multiply that by 2 times to give us the contribution of both flanges. Okay, so I'll update that slide there. A couple 2's not quite in the right spot. But once we have the effective moment of inertia, then we can just divide it by c, or multiply by 2 over d, and that's going to give us the effective section modulus that we use to calculate the moment resistance back here in accordance with CSAS 16. Does anyone have any questions about, or let me summarize quickly and then ask if there are any questions. When we're dealing with beams, we generally have a few different strengths to consider. One is My, one is MP. Class 1 and 2 sections can achieve MP, and we take the moment resistance as ZFY. Class 3 sections can achieve the yield moment, and we take the yield moment resistance as phi SFY. For class 4 sections, we get local buckling before we reach yield, and to account for that, we modify the section modulus in this way and use the effective section modulus with Fy to calculate a slightly reduced moment resistance for those types of sections. Does anyone have any questions about any of those concepts before we wrap things up for today? Last year I went over without an example, and I thought, okay, well, we don't need an example today. Today I'm under. I must have talked faster. Probably wanted to get back to my office. I feel a little sick today. But I'll leave it at that. There are some examples that you can follow on, actually, I don't even know if I have an example. Anyway, we're basically talking about phi ZFY versus phi SFY. What I should probably do is do like a class 1 versus 2 versus 3 kind of calculation. I'll put that in my notes for next time. On the quiz, you'll be basically asked to calculate the width to thickness ratio and determine if a beam is class 1, 2, or 3. If that causes you any issues, just let me know and I'll be happy to talk about it. But basically, other than that, now you should be able to differentiate between what a yield moment is and what a plastic moment is in terms of quantifying the resistance of steel beams. Determine the section class of a steel section based on its susceptibility to local buckling. And what class it is basically going to tell you whether or not you're using the yield moment, the plastic moment, or a smaller value for class 4 sections to calculate the factored moment resistance of a laterally supported beam. Does anyone have any questions about any of that stuff before wrapping things up? All right, well, we'll have a good break then. Hope you get some work done. I'll be available over the break if you have any questions about assignments, quizzes, or otherwise, so just send me an email and I'll get back to you. Otherwise, enjoy the time off, and we'll see you on Monday following the break.
I want to ask, do we need the handbook for the final exam?
Yeah. Yeah, that's